we have been working on, or we have developed using OpenSees. So let's go to the first one, which is kind of a brief description of some of the specific elements and models that are available in OpenSees for geotechnical applications. So when you look at that, first we have to think about the type of problems that we would like to solve using OpenSees. And I describe them in two levels. One is static or quasi-static problems, and dynamic or earthquake problems. For example, we would like to do the formation analysis in 1D, 2D, or 3D. Static consolidation is a typical problem that we deal with in geotechnical engineering. We would like to consider soil structure interaction problems, in particular shallow foundations, bearing capacity, settlement problems coming to mind, and also pile foundations. We would like to look at vertical and the lateral capacity. When we go into the dynamic or the earthquake problems, we look at free field analysis. Is a typical thing that we do in geotechnical engineering, and we would like to do that with a tool like OpenSees. Liquefaction has been an issue that cannot be addressed by many of the tools that are available currently or today. And of course, soil structure interaction problems, for example, the response of pile foundations, bridge bends, or actually the complete structures embedded in soils when they are subjected to an earthquake excitation. So what do we need? What are the things that we need in order to solve some of these problems? Well, because we are dealing with soil as a continuum, we need to look at solid elements to characterize the soil domain. We also need to be very careful about the boundary conditions, how to represent the boundary condition for this soil and the soil structure elements. We need robust and also efficient constitutive models to characterize the very nonlinear stress-strain response of soils under monotonic loads and also under cyclic loads. A lot of models are only useful for monotonic loads. Some models are useful for both or only for cyclic loading. And this is a big issue because soils are very, very nonlinear and present difficult characteristics to characterize. And of course, we need to have interface elements that allow us to capture the interaction between the soil and the adjacent structure. When you have a pile or a footing and the soil, how do you characterize that interface there could be problematic. And of course, everything else that you are learning here, like how to apply loads, how to impose the boundary condition, how to record results, how to perform the analysis. All those things I will not repeat because you have seen, you are looking at that in this course. So the elements that are available, finite elements for solids that are available, I separate into the single phase and the multi-phase elements and the zero length elements. When we look at material models, I look at the elastic models that are available, and also the elastoplastic continuum models, and also elastoplastic uniaxial models that could be used in order to characterize some of the response of the soil, or soil pile interaction, or soil structure interaction. And then for the boundary conditions, we will talk about equal DOF and how to address the problem of absorbent boundaries. So for the finite elements, for the single phase formulations, and that means to capture the response of the dry soil, or in order to do what is called total stress analysis, I don't need to separate in between the soil and the water. We look just as the behavior of the soil, dry soil or total stress analysis. Only one phase, which is the soil skeleton. Now, in many other situations, you want to separate the behavior of the soil from the behavior of the water. So in that case, you need to use a multi-phase formulation that captures the response of saturated soils, and in some cases, even partially saturated soils. But for those situations, you need more than one phase, two phases. One phase is the solid soil skeleton, and the other phase is the pore water. particularly when we are dealing with a saturated condition, we need only 2. If we want to consider the air, we need another phase also there. And the zero-length elements is used to capture the response between the solid and beam elements and to apply absorbent boundary conditions. So let's look at the simple elements that are available in OpenSees. For small deformations, we can use the two-dimensional quadrilateral elements. It's called the quad element. Or we can use the brick element in order to model the 3D situations. It's a standard brick in OpenSees that comes with 8 nodes or with 20 nodes. The 4 nodes the quad element comes with 4 nodes or with 9 nodes. How do you call that in OpenSees? Very simple. You use the command element, and then you put quad. Then you have a tag that allows you to identify the element that you're using, and then you put the nodes that are used to represent that element. These nodes have to be defined before the element is defined. You also define the thickness, the type of the two-dimensional element that you have, if it is plane stress or plane strain. Also the material tag that is associated with the element. And then you have some optional additional parameters like body forces, etc., that you have to include that you can include in the definition of the elements. Very simple. For multi-phase formulations, what we use is the fully coupled UP formulations. There has been some work done using what is called the UPU formulation in 3D and small deformations. Just to mention to you, UP means that we are going to track the displacement of the solid, and we are going to track the pore water pressure in the fluid. Now, more advanced formulations allows you to capture the displacement of the solid, the pressure in the fluid, and the displacement in the fluid relative to the solid too. So those are more advanced situations. Now, in order to do that, we have what they call the quad UP and the 9-4 quad UP that allows that capture this type of formulation, that include this formulation. Now, you see here that now the nodes, in addition to the degrees of freedom for the displacement, they also capture or record pore water pressures. This element, when it is presented like this, is not stable. So that's why in OpenSees you have what is called the 9-4 quad UP, where now the displacement are recorded in 9 nodes, and the pore water pressures are recorded only in the vertices, in 4 nodes. Okay, so this is a stable, an unconditional stable element that you can use. How do we represent that in OpenSees? Again, the command element, quad UP. You have to put an element tag that uniquely identifies the element. Then the nodes that are used to represent this element, the thickness, the type, the material type, very similar to the other one. But now you have to include additional information like the bulk modulus of the combined soil and water. You can also include the fluid mass density and the permeability in this element. And there are some additional also parameters like the body forces, etc., that you can include. Now, one thing that I want to mention is that the standard 2D and 3D solid elements use 4 integration points for the 2D case and 8 integration points for the standard brick element. And this has some problems. I would say they are not as efficient as other formulations could be. In particular, because of the number of Gauss points. So we have been looking at the possibility of using elements that have only 1 Gauss point instead of 4. That reduces the number of operations that you have to perform. Instead of performing all the operations at all the Gauss points, you perform the operations at only 1 Gauss point, both in the case of the 2D element and in the 3D element. Of course, that doing this is not something simple because you have to stabilize this element. There are spurious modes that you have, hourglass modes that you have to eliminate. I will mention a little bit more about this later in the second presentation. But I just want to mention that we have implemented this stabilized single point quad and stabilized single point brick elements in OpenSee. It's available in the code. And we are testing them. We have obtained very good results so far. We are in the 3D one. We are still doing some work because I am not completely certain that we are getting what we want there. So this is for a single phase. We have also extended that to the multi-phase elements. That means we have a stabilized single point quad UP that allows to represent the solid and the fluid, and also a stabilized single point brick UP that allows to characterize the behavior of the saturated soil in 3 dimensions. That's all I will say about the solid elements that are available right now in OpenSea. Let's talk now about the zero length element. The zero length element allows to connect 2 points at the same location or coordinates, and that will be very useful when you try to connect soil with maybe a structural element that could be a beam element. And in order to do that, what you use is the element zero length, and again you have to define the 2 nodes that connect this suppose node 3 here and node 6. And you have to define the type of material that will characterize that connection there, and in which directions these materials are going to be acting. So what you really are doing is to connect these 2 nodes that are in the same location with springs, and these springs can be nonlinear springs, and they can act in different directions. So if you're in 2D, you can have springs in 2 directions. If you're in 3D, you can have springs in the 3 directions. Now let's talk about the material models. And this is the bottleneck of many codes that are used in practice. And usually most of the computations happen at this level, and they happen at each Gauss point. So it's in general very important to have robust and efficient constitutive models. So in OpenSea, we have the conventional linear elastic material. It's an ND materials. ND means more than 1 dimension, n dimensions material. And it is used to characterize the response of the soil in its elastic state. Now, we know that the soil is not elastic. So in general, we are very limited using this material model. Now, in order to go into the plastic regime, we have to look at elastoplastic material models. They are still ND materials, and they are used to characterize the nonlinear stress-strain response of the soil. And also, in some cases, when we are trying to connect piles and soils, in practice has been very common to use springs. And these springs really characterize the nonlinear response between the soil and the structure. And they are usually given names like PY curves or TC curves, QC curves. So OpenSea has uniaxial material models that allows to characterize the interface response between the soil and the structural element. Okay. So they are there. So the ND material that is elastic is only for small deformations and in the elastic regime. It can be linear isotropic, non-linear isotropic, could be cross anisotropic. The most simple one is the linear isotropic, and that's the material that is available in OpenSea. And how do you define that in OpenSea? You have to say, use the command ND material. What type of ND material? Elastic isotropic. You give a material tag, an identificator for that material, and the elastic modulus and Poisson's ratio. Very simple. Now, when you go into the elastoplastic regime for small deformation still, the models that are currently operational in OpenSea are several. First, you have the very simple and classic material models, J2 plasticity of von Mises. That's the most conventional and simple constitutive model that you can use. You can include linear hardening, nonlinear hardening. It could be isotropic. It could be kinematic hardening. and so forth, but is limited. Limited because it doesn't capture everything that you want to know about the soil behavior. There is also a Drucker-Prager material, which I see as an extension of a J2 plasticity, because the only thing that it does is to include the effect of the sensitivity of the strength to the pressure. So the Drucker-Prager material is an extension of a J2 plasticity. And again, it's a classical material model that is in all the books, and we have implemented that in OpenSee. It's the first approximation that we can include there. Now, more specific materials for soils, you have the camp clay. If you're in geotechnical engineering, I'm sure that you know what is camp clay. It's a model that was developed in England, like in the 50s, and it's specific for clays. And there is one implementation of the camp clay material done here at Berkeley. We have been also working in one that is based on a bounding surface formulation. But it's, again, a classical material that is in all the books, particular geotechnical books. And then you have the multi-yield materials that were developed for geotechnical engineering in the United States, made popular in the United States by Prevost. And then El Gamal has been working a lot with these models. And actually, if he was here yesterday, I'm sure that he talked a lot about the multi-yield materials. And he also developed what is called a fluid solid porous material that allows to connect. It's a trick that he uses in order to impose what is called the incompressible condition. I don't suggest that to use that too much. Let me show you the von Mises model. This is a typical yield surface for a von Mises in a principal stress space. This is the type of stress-strain behavior that you can get. How do you call it in OpenSees? Again, ND material, multiple dimensions, not only one dimension. J2 plasticity is the name that you have to use. You need to have a tag to represent that model. And then you need the bulk modulus, you need the shear modulus, and then you need the initial yield condition, the maximum stress at infinity. And then you have to include these two other parameters, delta and H, are used to characterize the hardening behavior. Could be isotropic hardening, and I think the H is for kinematic hardening. Okay, now let's talk about the multi-yield materials. The problem with this one is that you cannot capture cyclic behavior. You can capture a monotonic behavior, but if you try to unload here, you would obtain elastic behavior all the way. And the reality is that when you unload the soil shows immediately as you unload plastic behavior again. So then this model cannot capture that behavior. And if you're doing seismic events, you will have cyclic incursions. And you want to characterize the nonlinearity in the unload. So in that case, never use a J2 model if you have that situation. So the multi-yield plasticity models that were initially established by Ross et al., and then they were made popular by Prevost and others. So in OpenSees, there are two types. One is the pressure-independent multi-yield model that is commonly used for total stress analysis. And then you also have the pressure-dependent multi-yield that captures well the response of the soil under earthquake excitation, and also, in this particular scenario, captures pretty well the response of the soil when it liquefies. And then you have this fluid solid porous material that was developed to couple the solid and the fluid phases when they didn't have at that moment the UP formulations. I wouldn't suggest to use that. Now, these models were developed by El Gamal, and you can go to this website. By the way, this presentation is going to be available for all of you if you want. So this is the website that you can use to get that information. And this is the type of response that you would get. You get a very nonlinear behavior. You may get what is called dilation, spikes of dilation, that are typical when you are modeling the behavior of a liquefiable soil. This is the idea that you have of a pressure-dependent multi-yield. You see all the yield surfaces, and as you move from one yield surface to the next, what happens is that the modulus changes, it reduces. And not only that, the yield surfaces move, so when you unload, you can also capture the cyclic behavior pretty well. Now, the thing is that if you want to define that material, you have to use, again, the ND command. Now you use the word pressure-dependent multi-yield, the material tag, the number of dimensions, because it could be two-dimensional or for a three-dimensional situation, and then you start with all the parameters: density, reference shear modulus, reference bulk modulus, friction angle, peak shear strength, reference stress, pressure dependent coefficient, phase transformation angle, contraction parameter, blah, blah, blah. So actually, what you need is 15 parameters. So where do you get all these parameters? That's the problem with most constitutive models for soils. I defend the models that have more than 3 parameters, because if you want to capture this behavior, believe me, you need more than 3 parameters. There is nothing you can do about that. But what you can do is, instead of torturing your students to calibrate parameters based on results that nobody understands or experiments that nobody understands, what you can do is to try to calibrate your model parameters for different densities. And that's what Kamal did. So he said, look, for a loose sand, that means relative densities in between 15 to 35, or medium dense, medium sand, medium dense, or dense. These are typical parameters that you can use for that particular model. And he also developed, unfortunately, a second version of the model that he called pressure-dependent multi-yield O2, and the parameters are different. So be careful if any of you is trying to use this. Make sure that you know what's the model that you are using. The pressure-dependent multi-yield O2 is newer, so I expect to see better results from that model than from the previous one. For the pressure-independent multi-yield, again, this is very commonly used for clays. And, oops. It should come here another table. I don't know why the table doesn't come again. But there is a table also that allows you to define all the different parameters for different clays that you may have, typical clays that you may have. And again, I just want to mention that the fluid solid porous material is a material that couples two phases. I will not mention too much about this because I don't think anybody is using the fluid solid materials anymore. So I don't think it's worth going there. Now, we are working right now on abound income clay at UW, and also we are working on the implementation of what is called the Mansari-Dafalias. The Mansari-Dafalias has been a model that was developed by Mansari and Dafalias at UC Davis. It has been implemented in several codes. FLAC is using it. I know that Professor Jeremy Davis, he has also been using it extensively. It seems to be getting some traction in the sense that people is starting to believe that the formulation is appropriate and that the parameters it's possible to define the parameters. So we are also working on the implementation of OpenSees of this model. Now, some additional commands that are here. One that are commonly used for the multi-yield materials. One is this that is called the update material stage. And these parameters are useful for the analysis. And what they do is that they allow you to do an elastic step analysis in order to generate maybe the effect of gravity. When you develop a model, you will have a mesh, and you would like to have the initial state of stress. you cannot set immediately the material as an elastoplastic and then boom, apply gravity in one step. If you want to do that, the correct way of doing that is to start with one layer of elements, very thin, then assume that the material is elastoplastic. Then apply another layer of soil and build your soil domain like it happened in nature. Very different is to start with a mesh and say, gravity, go. If you do that and you are using an elastoplastic constitutive model, your mesh will fly, because that is not possible. So one way to overcome that is to say, well, why don't we assume that the initial state is elastic? And once we have the elastic state of stress, then we switch the material to plastic. When you do that, all the variables will start shaking. What's happening here? But after a couple of steps, if you can, the system gets into equilibrium and the results are appropriate. So you have this command, update material state, that if it is, if the stage is 0, is elastic. If it is 1, is plastic. And if it is 2, is linear elastic by the function of the effective stress. The other one that you can use is update parameter. An update parameter is a useful parameter that allows you to change the material parameters, like the shear modulus or the bulk modulus or the strength. Why would you like to do that? Well, because maybe you're doing the analysis of a slope, and you want to know when you are going to have stability, what's the safety factor. So you start with an initial condition, and then you start reducing the strength until you get failure. So that type of analysis can be done, for example, updating your parameters. Or you may assume that the initial state is normal, and then you say, well, let's assume that the soil liquefied. How do I do that? Well, change the parameters for the parameters that correspond to a liquefied situation in some layer. You can do that using the update parameter. So it's very useful. The other thing that we have implemented is the idea of an initial state. When you have a soil profile, you model the soil profile with your elements. And when you apply gravity, what happens? Immediately you will have a deformation. But that deformation doesn't exist in nature. So when you continue your analysis, you will continue with an initial deformation that is not really there. And that can create problems when you try to connect this to a pile or where you have contact elements. So what we have done is to include a command that removes that deformation and includes that into the elements as an initial value that will be carried on in the analysis, but you will not see that. How do you do that? It's very easy. You just call the initial state analysis on, then you perform all your steps where you apply the load, and once you have applied gravity, you say, okay, initial state analysis off, and that immediately removes the displacements, and you can continue your analysis like if your soil was exactly at this level here. The other one that you want to know is these uniaxial models that allow you to characterize the response or the interface response between structures, for example, a pile, and the soil domain. How to connect the pile and this soil. Or actually, how to characterize the interface. That's what you are doing. So in order to do that, what we use is using these springs that they come in different directions. If it is in the horizontal direction, it's called the PY spring. If it is in the vertical direction, it's called the TC spring. And for the particular spring here at the bottom, it's called the QC spring. And these springs, or the nonlinearity of this spring, have been studied by many people experimentally. So what was done here in OpenSee is to implement uniaxial materials that capture that experimental response pretty well. So we have what is called the PY simple material, the TC simple material, the QC simple, and then there are some materials that are also used for the soil when it liquefies. For example, this is the type of PY behavior that you want to capture. In order to do that, you use the command uniaxial material py simple. And for py simple, you need a tag, very simple. And then you have to say, what type of soil do you have? Well, I have soil type 1, that means clay. We use the nonlinear model by Matlock, a person that did a lot of experiments. Oh, no, my soil type is 2. Oh, that's for a sand. Oh, and for sand, we use the American Petroleum Institute nonlinearity. So we can use that. And the model will know what it needs. What information that you need? You need the P ultimate, that's the value, the ultimate value here. You need what is called the Y50, which is the displacement at 50% of P ultimate. Also, you can have a drag resistant coefficient, C sub D, that allows the formation of gaps. And also, because you can do dynamic analysis, you can include a viscous coefficient that is included there. So no drag, no gap formation, you have this response. If you have the formation of gaps, you use a different coefficient, C sub D. Very simple. For the TC simple, again, you have parameters, but I don't want to entertain exactly the description of that. It's very simple. But they use different theories. For clay is the Rees-O'Neill, for sand is Mosher, and then for the Q simple, the theories are again based on Rees-O'Neill for clay, and Vijay-Berg, well, I cannot pronounce this. For sand, Vijay-Berg, yeah. Okay, so just want to mention that they are available in OpenSees. And for the when you have a liquefaction, there is also a little spring that is specific for those situations that allows to consider the degradation of the stiffness and the P ultimate, in particular the P ultimate, as the pore water pressures increase. And it's based on what is called the pore water pressure ratio. So when the pore water pressure ratio goes close to 1, then the P ultimate goes to 0. And that's a situation where you see that you have a soil element connected to a pile with one of these PY spring for liquefaction, and we apply this cyclic stress ratio. You see how the pore water pressures increase. When the pore water pressures get to a level that is equal to the initial confining pressure, then the pore water pressure ratio goes to 1. And when we have pore water pressures equal to 1, we say that we have liquefaction. So one interesting thing is that if you don't include the effect of liquefaction, you would obtain this response. But if after liquefaction you say, well, how much is my PY spring? The soil has liquefied. Do I have any strength here? How come that I have a strength when the soil has liquefied? Well, that is the response would be something like this: no strength at all. So you can do that using this particular element or this particular material model, the PY liquid, where the strength reduces as a factor of the pore water pressure ratio. Something to keep in mind. Now, how to include boundary conditions? Well, one of the things that we would like to do is to do a free field analysis. So we would like to have what is called periodic boundaries. That means that we would like to impose the same response here than on the other side. How do we do that? We use equal DOF in order to get this type of response, same lateral deformation. And that's what we like to get when we do free field analysis of soil. We don't want to have a column of soil that is moving like this. That doesn't represent, that's not what happens in the soil. If you see the soil here, it's going to move horizontally. It's not going to start rotating here. So that's why we have to use the equal DOF situation, where you say equal DOF, and of course, you have the master node, could be the master node here, and the slave node could be the other node. And you also specify in which degree of freedom is going to be equal DOF. For the absorbent boundaries, this is a big problem because you may have a structure here, and if you have a structure here that is oscillating, you may have, I don't know, a vibrator here. You will have waves that generate in the soil, and these waves, when they find a boundary here, will reflect. So what happens with that? The problem with that is that in reality, in the soil, this boundary doesn't exist. That boundary exists only in your model. not in the real soil. So you have to impose some boundary condition that absorbs all the energy that gets there. And for doing that, what we use is, again, very simple zero-length element and uniaxial materials, where we have these dashpots. And if you specify the properties of these dampers or dashpots properly, they absorb pretty well the energy, in particular when the energy is normal to the, is perpendicular to the, or is normal to the elements. So these coefficients for the dampers are based on the shear wave velocity and the P wave velocity and the density of the material that you have there. That's the most common way of doing things. The alternative way is to use real absorber boundaries, but they are not available in OpenSees. And that's just a small description of how to do that. Finally, how to model, if you're doing a 3D analysis of a pile, then you can't connect the pile with just one spring. I would need infinite number of springs here, and then I would have a problem because those springs, the PY springs, TC springs, they represent the whole pile. So how do I put many springs, each one representing a portion of the pile? That's a problem. So one alternative is to say, well, I want to model the pile in this way. I want to model the soil also, the three-dimensionality of the soil. So then you will need to account for the interface, maybe using a contact. And that's what we did. We implemented a contact element in OpenSees. We have what is called the two-dimensional node-to-line element. And we also implemented a 3D node-to-surface. What the element does is just to, there is a master node, there is a slave node, and what the element does is just to impose a constraint in the gap. So this gap can be whatever you want, but you can never have penetration. And by imposing that constraint, you can get the stiffness and all the matrices that are required in order to implement this element. We also implemented a pretty good one, pretty nice. I like this element in particular, that allows you to represent the contact between solid and a beam element. And why is that? Well, because in many cases you will represent your structure as beams. A lot of the things that I saw in the previous presentation today was modeling of structures where you use fiber sections, but in reality you're using beam elements. So for the piles, I also want to use a beam element. It's very convenient because I can get immediately the shear and the moments from the results. Now, if you want to use this, be careful because you will need to use a contact element that allows you to connect the solid domain with the beam element. And not only that, you need also to implement something that connects the end of the beam with the rest of the domain of the soil. So we developed what is called a 3D end beam to solid element that is available there. And again, it's very simple. This is a simple contact 2D. You need to define the elements that are the master nodes. You need also the slave node. Because it's based on what is called a Lagrangian formulation, you need a Lagrangian node. But we have recently implemented a penalty formulation that doesn't need to have that element there. And you have to define the material that will represent the frictional behavior between at the contact interface. And you have some tolerances here that are for the gap tolerance or for the force tolerance. If anybody is going to be using these elements, I recommend you to study a lot. Don't try to say, oh, I will use that element because it's available. Because you have to understand the limitations of these things. What can you do and what you can't do. And unless you understand what is going on, you don't need to know everything in the single detail, but you have to be a little bit careful about how to use these elements. And there are many other capabilities that are under development that I think that are not so important to mention here. So that's the end of my first presentation. Okay, so let's go to the second one. Okay, so why don't you stretch your arms and you say, okay, let's go to the next one, which is a little bit, I like this a little bit more. Okay, so questions about this? Yes?
First of all, Is the documentation available for the contact element?
Yes, the documentation is available in the wiki, in the OpenSee's wiki, okay, for all the contact elements, and you will need also to use a contact material to represent the interface. Okay.
One more about the absorbent boundary.
Yes.
You showed some formulation for the dash file.
Yes.
And the properties of the spring. Is it the same for 3D or for 3D?
It's the same for 3D. It's the same for 3D, but you will have three directions. Now, you have to be careful. This is based on Leismer. Which year, Boris? Leismer 1960, or even before that, 1950. And when the waves don't get to the boundary perpendicular, you will have reflections. So they're not perfect. They absorb, particularly when the waves go normal. And if you are really, so that means that what you need to do, if you're going to use that, put your boundaries far so that the reflections are not too much.
Should we use the body wave observation?
Yes.
Here it was
P waves and S. P waves and S waves. You can do both. Other questions? Okay. So now let's go into some examples. Some examples here. So first of all, I want to say, take advantage of TCL scripting. TCL is a scripting language. It's a benefit for OpenSees, and it's also a problem for OpenSees because now you are a slave of TCL in some sense. But the thing is that you can create scripts. And once you have created a script that is good, make it public so people can benefit from those scripts. And that's what we have been trying to do, is to develop some scripts using TCL that are specific for geotechnical applications. So we were looking at some of the typical cases. The other thing I want to mention is take advantage of pre and post processors. Because as soon as you go into 3D, or when you have a complex structure, you will notice that your MATLAB scripts that are used to develop your frames start to have problems. Because, oh, why don't we do that other building? Well, it's completely different, so your little script that you develop doesn't apply for that building. In soils, it's even worse, because the boundary conditions change completely. So pre and post processors have been developed to help you with this. And unfortunately, OpenSees doesn't have one. I have been using what is called GiD, which is a pre and post processor that was developed at the CIMNE. CIMNE is a center for International Center for Numerical Methods that is in Barcelona, and it's just one possible alternative. There are many other alternatives, and I will mention that because I've been using this one. It's not that expensive too. It's not public domain, but it's not that expensive. And I want to talk a little bit about some recent research projects that I developed using these things and GiD. In particular, I want to talk about the dynamic analysis of piles, analysis of a complete bridge system, and also the 3D analysis of piles that we are doing. So TCL is, as I mentioned, is an excellent tool to develop scripts for geotechnical applications. And the applications that we can use are, for example, laterally loaded pile foundation. That's similar to LPile. LPile is a commercial tool that is available, so we could do the same using OpenSees. One-dimensional consolidation, typical problem that we want to handle. Again, let's develop a little script that can be used for this. Total stress site response analysis. This is what Shake does. So can we do that using OpenSees? Then you can go into effective stress site response analysis, and now Shake cannot do that. So then it's very convenient to have something like OpenSees that allows you to do effective stress site response analysis of layer media. And again, there are some other codes available, but now you are reducing the number of codes that can do this. Then dynamic effective stress analysis of a slope. Now you're really reducing to finite element codes, for example, Plaxis, FLAC. You can use Abacus, of course. But OpenSees, now you are in the domain where things can only be done here. Excavation, excavation supported by cantilever sheet pile walls. So now you're dealing with problems that can only be handled using finite element tools, and OpenSees is one of those. So the idea was to develop a couple of these scripts that could help you starting with these type of things. If you go to the wiki, in the wiki you will see a list in the practical examples. You will see a list of geotechnical examples. So simulating a centrifuge test, laterally loaded pile foundation. And I imagine that Frank, he may have already talked about it. Have you talked about this, Frank, already? Okay, so one-dimensional consolidation, total stress and response analysis. So what we did is to do this type of analysis, and we described them a little bit. We included the input files. We tell here some of the problems that we face and how to solve. Now, don't think that by going here, say, I need to do a total stress or effective stress analysis. Let's use it directly. No, again, this is just a guide. Once you have the guide, you have to do your work. Okay? It's not going to work immediately, as Beta knows. Beta is a student at UW, so I know that she's doing this type of thing. So look at these things because I think they are useful. There are other useful TCL scripts here, the OpenSees website. Professor Jeremic at Davis developed a lot of these things in the past. UC San Diego has also some information there. We also have some other information available in our website, and of course in the wiki. For example, pseudostatic pile pushover analysis. Here we are modeling a pile using displacement beam column elements, and we are modeling the soil using the PY and the TC springs and the QC string at the bottom. We use zero-length elements in order to have these material models, and we use the =DOF command in order to connect this node here that represents the soil and the node that represents the pile. So it's very simple. And the script is done in such a way that you just say how deep is your soil, the type of soil conditions that you have, and it will generate the properties for all these little material models. And what we did is to compare the results in terms of displacement, the soil reaction, and the shear and the bending moments with another tool like LPile to see if we were getting results that were more or less similar. You can use that script, it's available. The other one-dimensional consolidation. Here, what we want to model is the consolidation of a soil column. It could be drain at the top and at the bottom, or only single drain only at the top. Here, what we use, because we want to model the soil and the water, we use the 9-4 quad UP element. We use a constant time series and a plane load pattern in order to apply a load here. And what you can model is how much is the development of pore water pressures and the dissipation of pore water pressures with time. And of course, you can measure the displacements as the consolidation happens. Again, the script was developed in such a way that you can change the properties, you can change the number of elements just by changing some variables at the beginning of the script. Again, if you want to use it, be careful. Just look what you are doing there. This is just results that show pore water pressures with time for a doubly drained situation. If it is single drainage, you see that the pore water pressures dissipate only at the surface and not at the bottom. And you see the evolution of the effective stresses. You start with very low effective stresses, and then you reach a final situation. And of course, you see how the settlements develop. If you have a doubly drain, the settlements happen much faster than if you have a single drain situation. And that's that typical thing that you want to do in geotechnical practice. That's why I developed this little thing to show that it's possible to do. Now, we have developed this stabilized single point element. You can also do that using that element. We don't have the input file. You can modify this input file for that particular purpose. Total stress analysis. Again, another typical application where we use these two-dimensional quad elements. It's just single quad. And we use equal DOF in order to impose the repeated boundaries, in order to represent the free field response. We use the pressure-dependent multi-yield and the pressure-independent multi-yield to represent the soil behavior here. And we also use a dashpot here and a viscous material in order to capture the compliant base. Sometimes what you want to model is the soil behavior up to the rock. But then the rock may be a soft rock, and you want to include the response or the effect of the soft rock. In order to do that, what you have to do is to include a compliance-based situation. For doing that, instead of an acceleration here, what you impose is a force, and the force is defined in terms of a velocity. All that is described in Leismer and Kuhlmeier, 1969. Very old stuff, very useful stuff, by the way. And it's described also in the wiki how to do that. Now, what we did is to develop again the script that you can modify the number of layers, and you define the properties of each layer. And we did it in such a way that was simple to use for everybody. And then we extended that. And I don't know if you have seen nees.hub, but if you are playing with nees.hub, you will notice that there is something that is called total stress analysis or effective stress analysis. Is this. What it does is graphically you can set all the information, and that little tool developed with Rapture, what it does is to generate the same input file. Okay, but the input file is also available in the wiki if you want to go directly to that. Again, we compared with Shake. Shake is the typical thing that is used. This is a surface, no, this is not a surface. Surface acceleration, no, this is the acceleration time history, and then this is the surface acceleration that you have in the model, from the model, and we compare OpenSee with ProShake and some other tools, both in terms of the time history and also the response spectra, to see if we were getting close or not close. We have to reproduce what other tools do in the regimes where these other tools are valid too, because Shake is not valid in some regimes. Be careful with that. The other thing that we did is to start moving a little bit beyond of the simple free field analysis. We wanted to model a free field analysis of a sloping ground, but now effective stress conditions. We consider not only the behavior of the soil, but the soil under a liquefied state. For that, we use, again, the 9-4 quad element to characterize the response of the fluid and the solid. We use the zero-length elements in order to get the boundary conditions correctly, and the equal DOF. And we use the pressure-dependent multi-yield O2 because that seems to be a good one to characterize the response of the liquefied soil. And again, what you have here is the stress strain, the stress path, and the pore water pressure at 3 different locations. So you see that the complex behavior, this is stress strain. At the surface, it's almost linear elastic. But look what happens when you are in the middle of the liquefiable layer, which is this. It's very, very nonlinear. And then when you are at the bottom down here, you have that the shear stresses are larger, but look, the response is still seems to be more linear on the linear elastic regime. Okay, so here what you have is just the deformation and the pore water pressures in the soil. Okay, so you see generation of pore water pressures high. When they are red, is liquefaction, so you see large deformations there. This can be also done using 3D analysis. Now, instead of using the 2-dimensional quad, what you use is the brick element. And you can do some funny things. For example, you can shake in that direction, but you can impose a slope in the other direction. So it's like having a slope that is going down, but you shake it in this direction. So you say, well, nothing will happen in that direction, the perpendicular. Well, if the soil liquefies, loses completely the strength, and boom, it's going to go down. So how to characterize the response? Then now you are in the 3D analysis, something that many codes cannot do. Now you are in the area where OpenSees becomes important. So here is the displacement in the red direction, and this is the displacement in the blue direction. Notice that not much happens until the pore water pressures are so high that the soil liquefies, and then you have a lot of deformation. So, and these are just snapshots of the displacement. I think I have here, yes. So shaking in that direction, and look at the displacement in that direction. Nothing happens at the beginning, liquefaction, and then boo, 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 this is going to start moving. So you have very large deformation. Actually, more permanent deformations than in the other direction. So that's why then you can start doing some funny, some interesting things. Of course, if you talk to beta, you say, well, this doesn't work. My results are not good. I don't know. So you send emails, and we are working. It's not easy. These things that seem to be easy are not so simple to do. And what we have been trying to do is to compare results with the 2D results, so to make sure that we have the response correctly. Now, let's go into more intense things. Now, let's look at the analysis of a two-dimensional slope. So it's not just a column. This is a two-dimensional problem. You have the slope. This yellow thing may be a liquefiable soil. How to model that? OK. So then you have to do two-dimensional elements. We have to model the boundary conditions, the compliance base. Again, you can model that using a dashpot. How to model these boundaries here on the left and the right edges. The way I've been doing that in OpenSees is to impose a free field response at both ends. How do I do that? Well, I model these columns, if you want. I impose the repeated boundary here, and I assume that the thickness of these columns is very high, so that the mass is large. So the mass is large here, and it's going to impose a deformation to this soil domain. Okay, so this soil domain is not going to do anything to that column because the thickness is so high that you have so much mass. Is this the best way to do that? Is one way of imposing free field response at both ends that I think it works. And I describe this also in the wiki. This is the mesh that we used. It doesn't matter that these elements are slender because we are using equal DOF. So the slenderness, the aspect ratio here is not so bad. These elements here that you have here are terrible, are horrible. I just put it here, but I just want to mention that creating meshes is an art. If you want to do finite elements, you have to become artists. That's the most important thing. Become an artist. How to develop a mesh? What I see in general is horrible stuff. Horrible. And that translates into your results. Your results become horrible. If your mesh is horrible, your results are horrible. So be careful with that. Learn how to become a good finite element artist. So here what we did is to impose an excitation down here at the bottom. And of course, you can start looking at pore water pressures in the liquefiable layer. And look, this is the stress-strain response up here. And this is the stress-strain response in some point in the liquefiable layer. So you see that now you need to capture the two-dimensionality of the event, and in different locations it's going to be very, very different. That's why you have to go two-dimensional or three-dimensional, and then OpenSees can be used for that. This is one where I was experimenting with, it's a different one, it's an excavation. Excavation is another typical problem, geotechnical problem. You have a soil domain, you build your sheet pile wall, or you have a soldier pile wall, and then you excavate. As you excavate, of course, that the soil is going to push here, you will have big demands on your wall. So how to capture that response? It's not that simple. Some codes can do that. Here what we use is the displacement beam column in order to, and the fiber section in order to capture the response, the nonlinear response of the wall. Then we use the beam contact two-dimensional in order to capture the interface. We use the initial state of stress command in order to apply gravity and then remove the displacement. That's important to characterize the interface there. We use the quad elements for the solid. We use the pressure-dependent multi-yield to capture the nonlinearity of the soil. And the soil elements to the right of the wall were removed or deleted in OpenSees as we did the analysis. So if you do that, you can start getting, for a particular situation like this, you get the moments, the shear demand, and you get also the moments. This is the initial contact forces before you apply you remove the elements. As you remove the elements, you see how these contact forces change. And again, you can plot, make plots of vertical stresses or horizontal stresses or shear stresses. And you can create also animations. So this is an animation of the deformation, the deformations that happen as you remove the soil elements. And again, the contours are for deformation here. Because we are using a beam element, you can look at how the demands in terms of shear and moments develop as you remove the elements. And that's pretty fun. I like this one. Because as you remove the elements, you can see how the shear demand and the bending moments develop, how the maximum develops and moves down. I thought that was it's very instructional and it's very useful also in practice. How we did that? Using GiD. GiD together with OpenSees was the tool to use. Again, the input files for these are all available in the wiki. Take advantage of TCL scripts, but you have a limit for this. So what did I want to say with this? So in some cases, it's difficult to create these TCL scripts. In particular, when you go to complex foundation configurations, 2, 3 pile groups, embankments, when you are dealing with wharfs, complex bridges, when you want to do 3D analysis, you are limited in what you can do with the TCL scripts that you can develop by hand. So that's why you need to go into the pre and post processors. And GiD, as I said, is one application. And what we did is to use GiD, as I mentioned. Now, if you try to use GiD and you think, oh, I will use GiD and use OpenSees. So I develop my mesh in GiD. Now, where is my input for OpenSees? No, you can't. So what we did is to develop what is called a problem type. A problem type that gets the information, is done in GiD, that takes the information, the CAD information or the element information, and outputs a file that can be customized as you want. So what we have done is to customize it so that it's for OpenSees. Now, we haven't included everything. What I have included is just the things that I want to use: solid elements, PY elements, contact elements. You're not going to find all the other commands that are available in OpenSees. That would require a huge effort to develop a problem type that is complete enough for that. But if you go there to that particular example, you will see descriptions on how to create the geometry, how to assign boundary conditions, in particular for a two-dimensional situation, how to assign the materials to the geometry, and how to generate the mesh and the OpenSees input file for typical two-dimensional geotechnical problems. So if you're doing a two-dimensional geotechnical problem that's similar to this, you can use that problem. That problem type is enough. So I included the problem type also in the wikis if you want to use it. Let me talk a little bit about some problems that we have been addressing using all these things. One is the dynamic analysis of piles. The other one is the analysis of a complete bridge, and 3D analysis of piles too. So this was a problem that actually I worked together with Boris on this one. It was the dynamic analysis of piles. We did centrifuge test. We did some model test in, I think it was Nevada? It was Nevada? Where did we do those? The big bridges. It was Nevada, I think. Vegas? No, Texas we did the bridge band, but the other models that we did, the bridge in, So now, what I did is to develop, or what we did is to develop very simple models. What I was interested in was trying to see, can we use a model that is as simple as this? Nothing. Soil column with springs, and this represents the bridge band. Or this bridge band with these two columns. Is this enough to capture some of the response? And the response I was interested in was the acceleration in the bridge band at the top, and maybe I was interested in bending moments along the pile. And so these are schematics of the centrifuge test for these bands. We apply an excitation here. We have a kinematic excitation that will impose an effect on the piles, as you imagine. And this is the model, the simple model that we use. And we use the pressure-dependent multi-yield for the solid, the PY springs implemented by Boulanger for the PY springs. And this is the cross-section for the pile. We use the fiber section. And what you have here are acceleration records for the bridge band here. In gray, you have what you got from the OpenSees, from centrifuge. And I think that the gray one is from OpenSees for a Northridge event that has a peak acceleration of 0.25 g. If you increase the peak acceleration to 0.74 g, you see that the simulations capture well the response at the top here. I am not saying that you can capture every detail, but the acceleration of the bridge band was captured pretty well. And if you look at the bending moments, OpenSees is the gray line, and the dots represent results from the centrifuge. You see that, at least also for the bending moments, they are pretty good. We also look at the response of a bridge. A complete bridge, we did that in the centrifuge. And this was my the simplest idealization of the whole thing. Three-dimensional, but you have these columns of soils that impose a deformation in that direction. In the perpendicular direction, I just put some springs. And very simple. I'm not saying that this is the best one. And if you look at what you get if you impose deformations here, so you see at least the three-dimensional response of the bridge is captured. Now the question is, how good is captured this response? And so let's go into that. So what I have here are the accelerations at the bridge bands. Again, centrifuge is gray and OpenSees is the black. You see that the response, at least in terms of the acceleration in that direction, was pretty good. That tells you that not always you need a very sophisticated model. It depends on what you're looking for. If you're looking at the response at the proximity, at the interface here between the pile and the soil, this model is going to be bad. But if you're just looking at accelerations at the top of the bridge band, the simpler models may be good enough. And again, you have here the bending moments. Let's look at this other example. This other example, I had to do a compromise. We wanted to model the whole bridge and the soil. So it was a 5-span bridge with a pile group foundation, with abutments, and with liquefiable soils with different thicknesses at different points. We wanted to consider lateral spreading. We wanted to consider different earthquake intensities. And we wanted to consider uncertainties. So you have a big problem here. And the big problem is because how do I model it? I have to compromise between the type of model that I can develop for this. So soil, pile, bridge, abutment interaction has to be modeled. We wanted to do the complete numerical simulation of the whole system using OpenSees. And we wanted to do also performance-based earthquake engineering analysis. That's why we were using uncertainties. And we wanted to develop some fragility curves, develop some fragility curves and some hazards curves using the PBE method that was developed here at Peer. So the thing is that if you want to do just one simulation, or a couple of simulations, I can put time on the model, developing an accurate three-dimensional model. But when you are doing performance-based analysis, you are talking about thousands of runs. And then my phase changes to this. Because if I have to do thousands of runs for different earthquakes, modeling the whole thing, I can be here for years. So again, this is the type of schematic of what we wanted to model. This is a two-dimensional view of the problem, and we decided to go two-dimensional. Now we put the structure. This is the structure. This is the pile. These are the pile foundations. They are different at the abutments than at all the other locations. Here, the light blue represents a clay. This yellow represents a liquefiable soil, very thick here, not so thick here. And this is a very dense material. Look at the cross-section for the bridge deck. These are the column configurations. This is the pile, the embankment, the abutment configuration, 6 times 1 pile group, 3 times 2 pile groups here. So how to model this? So we said, OK, we are going to start using springs and basic two-dimensional elements. So we use bearing spring to represent the bearing path, nonlinear. Also some nonlinear spring for the pile cap. Also some abutment reaction spring. And PY liquefiable and PY for the stiff clays. And also for the dry sand using the elements in OpenSees. For the clay, we use the pressure-independent material. For the sand and the liquefiable soil, we use the pressure-dependent multi-yield material. Then we use nonlinear fiber beam columns in order to represent the pile foundations. And we use, that's a good thing, a model of the bridge that had been developed by Mackey and Stochadinovics in 2003. So they have put a lot of time in developing of the bridge. And we could connect that with our soil. And again, look at the mesh. Very coarse mesh, bad mesh. Not the best one that we could have. But it was a compromise. I had to run thousands of these cases. I could not do that using a much more refined model. I was not using at that time parallel OpenSees, and I had real limitations. So now we use that, and we obtained some very good results. I want to just show you only one that indicates why to go and model the whole thing. So the thick liquefiable layer was on that side. The liquefiable layer here was much smaller. Here you see the pore water pressure ratios in black. So you see how thick the soil was, the liquefiable soil was, and the thickness there. Now, we observe here a lot of deformation, 90 centimeters in our predictions, only 20 centimeters in that location. So you say, oh, all the action is happening here. Well, because of how the pile was pushed and how it was connected to the other abutments, etc., most of the maximum demands were on that side. So that shows you that doing you could capture only that using a complete analysis of the whole bridge that is two-dimensional. If I had modeled only what happens here, I would have not obtained the maximum demands, because the maximum demands were on the other side. And if I had done only the analysis here, I would have not captured the effect of the other side. That's a situation where a 2D analysis becomes important. Finally, 3D analysis of piles. Again, we can model the pile using solid elements, and the soil using solid elements. Now, what's the problem with this? The problem with this is that usually what you are interested in is in the demand in the pile in terms of shear forces and moments, bending moments. How to get the bending moment from solid elements? If you go to your mechanics of materials, you can say, I can always calculate my stresses, I can integrate my stresses, I can calculate the equivalent bending moments at each level. I could do that, but it's problematic. Much easier to use a beam element, because the beam element or the beam elements give me directly as a response the shear forces and the bending moments. So now, if you do that, you have to be careful, because if you use a bending model, you still need to capture the three-dimensionality of the interface. How to do that? Well, we did that using what is called the beam contact element that we developed. And let me just show you what happens if I apply a load here at the top of the pile. If the beam contact, what it does is to maintain this gap that represents how much is the diameter of the pile. So if I push at the top, this element of pile is not going to move up to here to start pushing the soil. It's going to push the soil directly as you start pushing from it. So let me see if it does it. So you see, as I push, look how the soil is, how it's pushed in the lateral direction and also in the upward direction. So that shows that the element is working well. What we did is to validate this using, again, LPile and other tools to see that we were getting the low displacements, etc., that were appropriate. And then we started to do some analysis that you cannot do with simple codes. For example, the 3D pile analysis of a pile that is subjected to lateral spreading. So what do we have here? I have a pile, I have a soil, I have a liquefiable layer there. And that liquefiable layer will liquefy at one moment. There is a slope, and when it liquefies, it's going to try to move in the lateral direction. When that happens, the upper part will impose a demand on this pile that could be very large. So large that it may control the complete design of the pile. So we use a liquefiable layer using a reduced strength. We use unliquefied layers using dense sand characteristics. We use different combinations of thickness of the liquefiable layer and also the position. And also we use different pile diameters, 0.6, 1.37, 2.5. We use the displacement bin element. We use fiber sections to account for the nonlinearity of the pile, and so forth. This shows a plan view from here where you see the pile, and you see here the location of the interface elements. And the boundary conditions that we apply is displacements here at the top and linear displacement on the boundaries in order to simulate what happens when the soil liquefies. So by doing that, this mass of soil, what we'll do is to impose a load into the pile, and then you can get the demands in terms of shears and moments. You can get the shear demand, and also you can get the bending demand there. You can also start getting some other things like the contact forces. Oh, this is interesting because I can get the contact forces around the pile or in one particular direction. Oh, this is useful because now I can start getting numerical experiments that allow me to get PY curves. All these PY curves that are commonly used in practice have been developed from experiments. Experiments where the piles were pushed at the surface here. So this allows me to do the same experiments or experiments that you cannot perform in practice in the field experimentally. So I can do numerical experiments that may allow me to get some other stuff. So what you do is, in general, you get the contact forces. From the contact forces, you get the force that corresponds to each displacement. And if you have different displacements, you can get the forces. You can reproduce PY curves at different locations and for different kinematics. And this shows you, for example, how is the effect of a liquefiable layer on the PY characteristics parameters. Here in blue, I think, in blue, I am showing how the P ultimate changes with depth if there is no liquefiable layer. And in this side, we have the stiffness. It's not the P ultimate, but the stiffness. And the red tells you how is the P ultimate if you have a liquefiable layer. And what is important here is to notice how the P ultimate in the liquefiable layer is going to be small, but how the P ultimate also is affected in the vicinity of the liquefiable layer. Something that Caltrans has been interested for a long time. So we were trying to investigate that effect numerically. Very good. I thought it was a very, very interesting process. You can also look at shear diagrams and bending moment diagrams, and you can try to see how much is the maximum bending moment for different deformations, and where is the maximum bending moment. Another thing Caltrans is interested to know how much are the bending moments and the location of the maximum bending moments. So another thing that we could do using this thing. Just want to mention this idea of the single point, stabilized single point elements. And what happens, as I mentioned, is that the integration of a typical 4-node quadrilateral elements involves 4 integration points. If this could be reduced to only one single integration point, then you are doing 4 times less of the work, or 8 times less the work in a 3-dimensional case. Can be done that? Well, the problem is that there are issues that must be overcome when you use a single point. In particular, the stiffness matrix becomes rank deficient. That's a problem. And that leads to what is called the hourglass spurious modes. So you have to deal with that problem first. So stabilization techniques can be used to overcome this rank deficiency. And we use that. And a single point integration element with an assumed strain hourglass stabilization was implemented in OpenSees, and you can use that nowadays. Let me show you, we did a free field analysis, and this is a free field analysis of a total stress free field analysis. And using the quad elements, the execution time for that particular problem, we had 150 elements, was 330 seconds. When we use the stabilized single point, we reduce that to 146 seconds, almost half. So that's a benefit that you can get. So I recommend to use it. Try to use it because it's available and seems to be giving very good results. Now, when you would try to do a liquefaction analysis, you have to include now the water, and as I mentioned, we can use these fully coupled formulations, in particular the work by Shiomi and Sienkiewicz is very cited everywhere. So what we did is to extend the SSP quad in order to include a fluid saturated condition, porous media, and we developed the SSP quad UP. Now, again, we have some other problems here. And one of the problems is that when you are dealing with a saturated soil, then the water is incompressible. And if you have very low permeability, you are in the incompressibility region. And near the incompressibility impermeable limit, the elements do not satisfy what is called the INSUB condition. So what you have to do is to stabilize the pressure field. And what we did is to use a consistent stabilization term that is added to the system in order to account for this problem. And we did an analysis again. This is a typical problem that appears in all the papers that Ronnie Borja does at Stanford. So, and it's a good one because it models a 2-dimensional problem that it could be a saturated soil, you have a load. It really triggers a lot of the phenomenon that you are interested in. So we reproduce that problem. We'll try to see what happens if you use just the unstabilized single point quad UP. Without the stabilization for the INSUB condition, you don't get very good results. How do I know? Well, because if I use I don't have it here. If I use the 9-4 quad element, I would get a much better response. Now, if I use, this is 9-node quad element, and this is the stabilized one. So you see that the comparison, the 9-4 node is stable. So I don't need to do anything to that. So it's a good element to compare with. And you see that the stabilized SSP quad UP captures more or less the response. Now, what's the benefit here? The benefit is I don't need to use 9 nodes and 4 nodes for the pressure. And the second thing is that I have only 1 integration point. This simplifies a lot of things, not only for modeling the soil, but also for connecting the soil mesh to the pile elements. This simplifies a lot of the problems that you may have. Not only that, notice the execution time. If you use just the SSP quad, this example ran in 4 minutes. And if you use just the conventional quad UP or the 9-4 quad, look at the time that is required to run. So you see the benefit in terms of speed for this. Finally, you can not only do one pile in a little sloping or not sloping ground, you can also start now analyzing the effect of the sloping ground into the behavior of the pile. You can also start doing analysis of a bridge band, complete bridge band embedded into the soil domain. And lately, we have been working on developing a model that represents the response of a bridge abutment. So we are looking at the effect of the three-dimensional effects of the embankment on the forces that are applied on the piles. So you see here the embankment, you see here the abutment, you see here a footing. If you want to see the footing better, this is the footing. You see the piles. We had a liquefiable layer here that is the blue. And here I just removed some parts so that you can see the piles. And we were going to impose a deformation that is typical of a lateral spreading. And what we want to know is the effect of the embankment, the three-dimensional embankment into the response of the piles. This is not easy. This model has around 200,000. It's not the best mesh that we can have. This is, again, I am struggling with a mesh that we could use. We have a more refined mesh, and then we have started with this one. When I say that meshing is an art, the best thing that you can do is to develop a mesh that you can refine. That's what you have to do. So what we did is to put a lot of time in trying to develop a mesh where these elements can be made smaller. So this has around 150 to 200,000 degrees of freedom. I tried to run this in a conventional machine. We are using Enterprise Linux, Red Hat Enterprise, and conventional OpenSees. It takes 7 days to run for around 400 steps. Then we switched to OpenSees.SP and the MAMP solver. And we have seen a great improvement. This is tough to do. Let me show you something just to finish, because this is the last one, I think. And I just want to show you, let me show you GiD. This is GiD. So I just want to mention, so in GiD what you define is geometries. So you can define these geometries here. And this is what really takes time here. So, and it's not that simple to define this geometry. So, for example, let me see, what do I have here? I can, yes. So I can put only the pile. So you see the pile. These are not the elements. These are sections where I will define the pile elements. Look at the pile cap. The pile cap is there. So you can see, this is just to define the geometries here. Okay? Elements will be defined inside each one of these little volumes. Okay? So, again, here there is around, I would say, almost 3 weeks of work. Then you have the embankment. Let me remove the embankment. Let me put the abutment. The abutment is there. The embankment is there. And then you can start adding all the other elements. Now, let me show you how does the mesh look like. This is how the mesh looks like. So you can't really do this by hand. That's my message here. So even if I look at, let me show you here again. I will clear everything, and I will put just the piles. And I will put just the pile cap. So these are now we are talking about the elements. And don't worry, it seems that there are no connections here. It seems that there are no connections, but these elements are closed here. These elements here are closed. It's the graphical tool that is not showing that. And so it's a difficult mesh. And the piles, abutment, and then of course you have all the other parts. So this is what you can do with GiD. And then after that you can call the post-processor. And here I just have, I think, only gravity and maybe one low step. These files are big. I am running Windows XP here. It's pretty old. But then now here you see a little bit better the mesh. And you can again see, for example, I can remove the layer and I can remove the very loose. So if I rotate this, so you can see the piles. And then I can start looking at, for example, let me show you the formation. The formation is going to show something huge, I imagine. Yeah, so, but the magnification is 210%, so let's put a 5 times magnification. So you see almost nothing. But then you can start looking at contours, and you can look at the stresses. I don't know, the sigma z, I think, is the vertical one. No, that's not. And I don't want that. I don't want this. I want to go here. So these are the vertical stresses at the beginning. And again, if I put, these are all the elements. So you see the distribution of vertical stresses due to gravity. So that's the type of thing that we look at. And yes, we start looking at problems. What is happening here? What's happening there? Why do you have the stress concentration? Well, because you have, what you have here is an abutment, and you have the footing. If I remove the embankment, yes, you will see there. Yes, you will see the structure. So what is happening is that due to gravity, there are some slight movements, and this thing is under stress. So we have to deal with those things and try to reproduce as well as we can the initial conditions, so that then once we have the initial conditions, we can apply the lateral loads and go from there. Once we have a model that works at this level of coarseness, then you can, our plan is to go with a more refined model where we can wait maybe, now this is running in 1 day. And we can wait maybe 3 or 4 days in order to get results. But at least you start with a coarse mesh, and then you go into a more refined one. So that's more or less all I wanna mention and I wanna show today. So if you have questions, please let me know.
I have a question on the ND material. As you showed, we use ND material pressure dependent for sand and drain condition, right? So what if we have sand but it's in undrained condition? Should we use?
So what you should use there is a pressure dependent multi-yield, the O2 or the original one, but you have to use the quad UP. Now, if you're going to use a multi-phase, if you either use the stabilized single point UP or use the 9-4 UP. Don't use I would not suggest to use the quad UP element because it's not stable. Now what happens is that soils have permeability, and because they are permeable, the permeability stabilizes things. So I have seen a lot of people using directly the quad UP. Oh, the quad UP works well. Yes, because of the values of permeability that you're using, but it's very dangerous. I would prefer to use a stabilized one than. It's simple, because you will notice that your advisor will tell you, no, use the 9-4, and you will say, no, that is the quad. The quad is much simpler. I don't need to have 9 nodes and 4 pressure nodes. Who wants to go into that mess? So the reality is that if you know what is going on behind the element, you will realize immediately that the quad UP can have problems. The stabilized one that we developed, we are still testing it. You are welcome to use it, but don't kill me if you find a problem, because we are still testing it.
And so the tables that is recommended in the manual is not useful, right?
Yeah, it's useful.
Because it's for sand in drain condition.
No, it's not for sand in drain condition. It's for sands. It's for sands. I think that I have bored everybody. Okay.
Pedro?
Okay, welcome.